Okay, so here we go. So what we're going to show right now is that edge chromatic number of G is less than or equal to the maximum degree of G plus 1, specifically if G is simple. So let's consider. So the approach to this proof is that we're essentially going to consider some possible existing edge coloring on some subgraph and essentially just extending that coloring specifically by a single edge while still retaining the bound essentially. So let's just consider F as a delta G plus 1 coloring, edge coloring specifically, obviously, of some subgraph H of G. And so, like I said, goal or the approach essentially of the proof is extend, more so iteratively extend F to all of G. So we're going to set this up by considering one single edge and kind of going from there. So let's consider some vertex U is going to be the primary vertex we consider. So U, some within the vertex set of G, and uncolored edge. Let's just say equals U and V within the edge set of G. So the goal here again is to extend the current coloring, which we can consider as delta G plus 1, to that certain edge. And so this is kind of like an algorithmic approach for this proof, more or less. So we're considering that vertex U, that specific edge that we're going to color, and we can consider F as this existing coloring, because obviously it could just be, say, a coloring on one single edge. Obviously that will be less than or equal to the maximum degree plus 1. So in the neighborhood of our vertex U, so the neighborhood of U, there are some number of existing colors is what we're assuming. There are some number of colors existing, but more specifically, there's going to be some colors missing. So let's focus on there are some number of missing colors specifically. Within the neighborhood, obviously there must be, because if we're considering, say, U as the maximum degree vertex, it can have at most delta G colors in its immediate neighborhood. But the issue, like we saw before, is we can't just naively say color one edge, because we have to consider the other endpoint of that specific edge. So in our neighborhood, there are some number of missing colors. So first, essentially, let's consider A naught is one such missing color. So let's kind of look at how we're setting this up specifically. So we're going to be considering U's neighborhood, obviously, U. So we have our vertex V, and then we're going to have some number of vertices V1, V2, V3, ... So at each of these vertices, there's some missing color. And the reason why is, well, without loss of generality, we can structure the neighborhood in this way, and we'll kind of explain why in a second. So A naught is missing in the neighborhood of U, is what we're assuming. At V, which is also, we could also equivalently, just the way we're structuring here, call this V naught, but you know. So this one is missing A1, missing A2, 2, and then dot dot dot. As we have set up here, essentially we're just considering, like we said, consider neighborhood of U, and generally speaking, AI plus 1 is the color missing at VI, which is within the neighborhood of V. And so the reason why we're setting this up in this way specifically is, let's consider the fact that if A1 is missing at V0 and, or V, just our V, well, we can just call that V0 just for consistency here and to go along with how we essentially set it up. And A1 is not within the neighborhood of U, then we can simply color our U and V0 with A1. So that's essentially why this is set up in this certain way, because trivially, if V0 is missing the color A1 and U is also missing the color A1 within its neighborhood, then essentially we can simply color it that way. So one thing I didn't mention is that these vertices, these edges are colored in this specific way. Yeah, I didn't make that exactly clear, but that's essentially the intention. That's probably the most important thing. Let's make that explicit. AI is the color on the edge U, V, I. So essentially that's how we have missing here. And we're assuming that, say, V0 has color A0 within its neighborhood. Otherwise, we could again trivially color U, V0 with just that A0 color. So that is our uncolored edge as we have it right now. So the structure of how we have this all set up is essentially dependent on this basic idea. So if in fact this vertex, say V1, if there wasn't another A2 within the neighborhood of U, we could trivially just replace this A1 with A2 and then label U V0 or U V0 edge with A1. Likewise, the argument continues. So our V2 missing, let's get rid of that, A1. So this one is missing A3. So the idea here is if there wasn't some A3 within U's neighborhood, we could just trivially replace this with A2, which we know is already missing at the neighborhood of V1. And then, again, just trivially color that edge with A1. So I kind of have this iterative process. So we're assuming that this structure exists for all of U's neighborhood is the basic idea in terms of how this is set up, because trivially, if it didn't, then we could just recolor and essentially we'd be done. So that would be kind of our trivial case in that instance. So we're considering the case where the neighborhood is set up in this very explicit way, where essentially we have, without loss of generality, A0 missing at U, A1 missing at V0, etc., with the rest of U's neighborhood colored. Generally, if AI is missing at U, use AI on the edge U, VI minus 1, and we'll rotate colors down to that edge U and V0. So this is basically more or less going to be considered our trivial case. And the reason why this is more so our trivial case, like I said, is that so we have two options here. either we have this explicit setup, and we can rotate colors down. So we're guaranteed that this is possible, basically because we have delta G plus 1 max colors. But this is where it gets tricky. So we didn't explicitly note this possibility before, or a color repeats. So this is kind of our case 1, and this is our case 2. So our case 1, again, if we have kind of the structured setup here, eventually, up to this ... essentially, because we only have delta G plus 1 maximum colors possible, and we have a neighborhood of delta G, then, there's going to be a case where we are able to eventually do this rotation of the colors all the way down to the missing color, or the missing edge, in terms of edge coloring. So that's assuming that, we have every single vertex in the neighborhood is missing some specific color. But our case 2 is a color within that, within some neighborhood of a vertex within the neighborhood of U has some missing color that repeats. So this is going to be, so we're going to consider our, this VL, which is going to be, is the first, essentially the first repeating color, or the first vertex with a repeating missing color. It's the first vertex with missing color essentially on, if we consider, on A1 ... up to AL. So essentially we run into up here some VL that is also missing some color A, X, which is equal to some color missing within, the rest of the color set, essentially. So, we'll also consider that, so VL is vertex within the color, right? So we'll say that this color, we'll define this color to be A sub K. And so as we've defined what we had before, A sub K is also missing at VK minus 1 and appears on the edge on edge U, V, K. So let's take another look at this specific setup for our case 2. So we have our U again, we have our V naught slash V. So U missing A naught. We're assuming V naught is missing V or A1. And then, our V1 and ... Then we have some vertex, as we have here, vertex V sub K minus 1. This is missing A sub K. Then we got another ... And then we got our V sub L. So our V sub L, which is also missing A sub K. So this is essentially the setup that we had before, and we have A1 here, and or A sub K right here, and color A sub L is going to be on that specific edge. So there's a couple things we should know. First, A naught also appears in the neighborhood of V sub L, because otherwise we could just replace the color there, or just we could color U V L with A naught and rotate colors all the way down to our edge V naught. Let's keep it consistent, U V naught. So essentially the idea here is that this is also, let's do red for this. This is missing A naught, because if it wasn't, then we could recolor this A naught, recolor this AL minus 1 dot 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 dot, and essentially color this A1, A2, A3 dot dot dot, etc. And so we have this kind of shifting down again. Yeah, so again, we're assuming, like we had before, we said that the V naught is missing A1. The implication there is it also is missing, or it also contains in its neighborhood A naught, because again, otherwise we could just trivially color it there. Okay. Now we're going to bust out our old friend, alternating path. So here we'll define P. So we've used this technique several times now, this kind of maximal path argument, kind of an extremal argument to an extent, in a certain way. I loosely define it that way. So define P as a maximal alternating path of edges colored A naught, comma, A, K from V sub L. So we're assuming, if we're going to say this is our color, oops, so here essentially the idea is we have something along the lines of this, where we have A naught, A, K, A naught, and etc. dot dot dot. That's our P, essentially. This is our P. So let's think about what happens when we consider this P as a maximal alternating path specifically. So if P reaches, so here let's call this case 2B. P reaches our V sub K, rotate our colors down, from that V sub K minus 1, and swap colors on P. The idea here is if we reach some vertex on this path, say V sub K, looks like this should be K minus 1, because this color is A sub K. So essentially, let's swap this. Essentially, we have A naught, and then we have our A sub K. So the idea here is we instead essentially just rotate colors down. So we get rid of the AK here. This is now AK. The next would be AK minus 1, or this is AK, and then this AK minus 1 rotates down, etc., etc. And so what do we have? Now, as we saw, we rotate colors down from VK minus 1, then swap our colors on P. So what does that give us? Essentially, we now have a k, a naught, a k, and effectively now instead of having this a naught over here, we can just color that as a naught. So, and that is now a k, and this is a naught, etc., etc. So the idea is that we simply, this path P, if it does in fact reach that vertex vk, we can essentially kind of do this structured swap and rotation. Then swap colors on P, and then let's make it explicit. We'll color our vertex, what is it, V sub L and U, color that edge with a naught. Moving on to our case 2, is that case 2B? So that should just be case 2A. There we go. This is our actual case 2B. So our case 2B, if P reaches, so P reaches Vk minus 1, so instead of reaching it, our Vk specifically now reaches Vk minus 1, because we have the assumption that a naught is within the neighborhood of that vertex. So if P reaches Vk minus 1, essentially all we can do is rotate colors down and then swap on our P. So in this instance, this a naught is now over the extra long edge going all the way over there. So what are we doing? We're doing a swap here, 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 and then we're going to specifically be coloring right like so. So now a naught is on that Vk minus 1, Vk minus, or the AK minus 1, now over there, and then rotate, etc. A1 right there. So we did swap on P, then rotation down Vk minus 1. All right, let's get back to where we were. Okay, back there. All right. So rotate colors down, swap on P, and then again, make it explicit. Color Vk minus 1 U with a naught. And then we'd be done in that instance. So moving on, case 2C. So here essentially is the else case. If P reaches anywhere else, we essentially rotate down. We can rotate down from our V sub L, place a naught on that edge U VL after swap on P. In this case captures pretty much anywhere else the path could go. So it could say either just end somewhere else in the graph, or it could end, without loss of generality, like at edge or at vertex V1 with this A naught, doesn't matter. Essentially, we just rotate down from our A sub L and do our standard swap approach, effectively speaking. Place a naught on our U V sub L and then do a swap. So let's do that. Swap, 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 swap. Kind of getting, let's make it more, a little better than that. There we go. And there we go, there we go, there we go, there we go. A naught. Or even if it ended up elsewhere in the graph, it doesn't really matter. the idea is the same. We can still do the swap as is and end up with, instead of a sub k, hypothetically, if v1 was missing a sub k, hypothetically in its neighborhood, or, if it was missing anything else, doesn't really matter, or it could end up elsewhere within the graph. But I mean, the argument is the same no matter what. We do this, and then we do our rotation of our colors all the way back down. So now RU V0 is colored. So essentially, at the end of the day here, regardless of which case, we have increased our coloring, our specifically chi prime of G, or let's say our delta G plus 1 coloring by 1 edge. So iterating gives us delta G plus 1 coloring plus 1 coloring on the entirety of G. So the takeaway here is that the edge chromatic number of G equals delta G or delta G plus 1. So that's the primary takeaway here of this proof. Again, this one, the argument it's sort of algorithmic, sort of extremal in a way, so it's kind of all over the place, kind of tough to follow. But, the takeaway is relatively interesting in terms of, this specific bound that we have right here. So this upper bound and obviously the lower bound that we have, greater than or equal to delta G, taken together give us that final bound down here.